Welcome to the EPG Pathashala, the lecture series in computer science for the PG program, and this is the compiler design course where we are going to look at the 28th module, which is going to discuss about code generator, an introduction to it, and a small introduction to what is called as basic blocks. The objectives of this module are to understand the issues in generating code, to know about the concepts of basic blocks and flow graphs, which is essential in generating code for a final output in terms of assembly level code or in terms of machine code. So, so far we have discussed the front end completely, where we have talked about the lexical phase, the syntactic phase and semantic phase. We also after doing that, we also did an intermediate code generation, where we have converted the representation into some form which is simpler for the code generator algorithm to take a look at it and generate final code, and all these will basically be accessing your symbol table. So, we have brought the input, that is the high level programming languages input, into a representation which is going to be very helpful for the code generator to finally generate code. Then what is the big deal in issues and things like that. So, how the fundamental issue itself is how do we give input to the code generator, okay. So, and then we should decide on what is going to be your target machine, okay, and then we should we should know the instruction set of the target machine. Do we want to have it as a assembly level code, or do we have to have it as a byte code itself? That again is going to be a big question. And then after that, will I place my optimizer here at the intermediate level, or will I place the optimizer after the code generator is going to be a final level? So, the position of optimizer should also be decided now itself, okay. So, these issues basically are going to be really threatening us for developing algorithms that is going to be useful for code generation. So, these three phases are basically called as the front end or the analysis phase, and then finally after doing this we will go to the intermediate code, and that onwards it is called as the synthesis phase. So, analysis is looking at the input code, and here we are finally generating the final code which corresponds to the target language, which can be either assembly level language or it could be your byte code itself, okay. So, the code generation, code produced must be by the compiler must be correct. Again, characteristics of good code. The source to target program transformation should be semantically preserving, that is, it should not alter the meaning. So, our intermediate code so far, the 3 address code basically has ensured that the abstract syntax tree or the quadruple, or the DAG has basically converted to a final 3 address code representation which is going to be correct semantically, obeying the rules of your obeying the meaning, preserving the meaning conveyed by your input high level language. Now, this translation from the intermediate code to the final code should also basically be semantically preserving, and the code produced by the compiler must be of high quality. It should not be just spilling beans over everything, something like that. It should be highly target specific, mission specific, okay, effectively using the resource of a particular target mission, and the heuristic techniques that basically is followed should also be ensuring that you have a good optimal code and rather suboptimal code, because an optimal code generation is going to be undesirable problem. So, we will have to ensure that whatever code is generated at the maximum should basically be optimally generated. So, looking at the issues in the design of code generator, so these are the characteristics of the code. Basically, it should be correct, it should be semantically preserving the input, and it should basically be of highly optimal, okay. So, though we do not look at optimality at the first instinct, we have to ensure that even at the basic level it is optimal to a certain extent, okay. So, with that in mind, what are the problems one could face in designing a code generator, okay. The first one is the input to the code generator. That itself is a problem. That is, should I give the input as a quadruple, or should it be a triple, or should it be a pentaple, or can I change it? Should it be an abstract syntax tree? Should it be a DAG? So many questions are there. Okay. And second one is target program. Should it be bytecode? Should it be assembly level code? If it is assembly level code, what is the architecture? If it is bytecode, what is the size? How do I format it? Okay, all these things are basically issues. And memory management. Okay, how many registers? How much of memory is basically available? What is the size of your registers? All these things are going to be question. Again, how many registers will I use? Again, that's going to be a question. And instruction selection, you have a set of available instructions. Can I use one instruction in place of the other instruction? Okay, which one will I choose at a particular point of time? That is going to be the next issue. Then register allocation. Primary and very challenging task is register allocation. You have limited number of registers, but you have infinite number of variables. So how do I map this limitedness to the unlimitedness basically? So that is what we are looking at as issues. So your code generator should be in a position to handle all these issues and try to generate optimal code at the maximum extent possible. So the first one is input to the code generator. The intermediate representation of the source program is typically in terms of a linear representation, which is a postfix representation, or it could be tables in terms of quadruples, triples or indirect triples, or it could have a non-linear representation as an abstract syntax tree or DAG. In addition, I need also symbol table information to give it to the code generator. Okay. So how do I give this to the code generator such that basically gets the input, maps it and generates your final code? That's going to be a challenging task. The next one is target program code. The backend code generator of a compiler may generate different forms of code depending upon the requirements. It could basically generate an absolute machine code, which is an executable by itself, or it could be a relocatable machine code where you will have an object file which will be finally loaded by the loader and then linked by the linker for execution. So will it be like that, or can it be pertaining to an assembly level language? If that is a scenario, I should know what is going to be my instruction set and what is the instruction format, instruction size should also be available here. Or should I generate code at the bytecode in terms of the interpreters like your Java virtual machine, etc. So this is again a question. So you have to decide on this particular task before generating code. And the target machine. Implementing code generation requires a thorough understanding of the target machine architecture and its instruction set. So our hypothetical machine, we are going to consider this as per the textbook followed by Aho, Sethi, Ullman is, it is byte addressable where the word corresponds to 4 bytes. It has got n general purpose registers like R0, R1, etc. up to Rn minus 1, and the instructions are the form are two forms instructions where you will have the opcode and followed by source followed by destination. So this will be the address instruction format. It will have an opcode, source information and then finally destination information. So this will be this is what we are going to consider in this particular chapter for generating code. So opcodes which we typically use here are a move, add, sub. Move is for moving content from one location to from source to destination typically. Add will be add content of source to destination and the result will be in the destination of course. Subtract will be subtract content of source from destination, result will be in destination. So that is your convention which is going to be followed here. And we are going to follow the following addressing modes, where addressing modes can be absolute, register based, indexed, indirect register or indirect indexed, or it could be a literal, okay, which is immediate addressing basically. So here the form which is going to be used is absolute means its memory M, and register means you are going to use R, indexed means C of R, where the interpretation is C plus contents of R. So whatever the value is given here, that value plus the contents of R will be used for fetching up information from that particular location. So how do I compute the addresses? Like this. And then star R means contents of R. So R will basically have a particular value or an address. So contents of R will refer to the address. So you go to that address and get your information. Star CR, this is a combination of these two. So which is nothing but contents of, okay, star CR means what? Contents of R. Okay. Now I have a star C of R. What does C of R means? C plus contents of R. So, it is content of, that is using this one, it is content of R, but what is R? R by itself is now C of R. So, content of C plus contents of R. So, how do I go it? I have to go to contents of R, get an address. This is your offset C, offset it, and then go to its location to get your address. Okay, and then that is going to be your thing. The last one is literal, which is hash C, which is available as part of the instruction itself. Okay, so here address is not going to be applicable at all. Now, what is the cost involved? Added cost involved in addition to your operating cost. So, here it is a memory. So, you are going to, if it involves memory, it is going to be costing you 1 more. Okay. So, added cost is 1. Register means there is no cost involved here, 0. The third one is C plus contents of R. Again, it is going to be computing the address. So, it is going to be involving 1. You are going to fetch from some address. Contents of R is again no, because it is available in the register itself. Okay. And then this was going to cost you 1, and this is going to cost you again 1, because it is anyway available as part of the instruction itself. Now, the instruction selection cost is very important for when we are looking at instruction selection. Cost is going to be a primary factor in addition to instruction choice. Okay. First one is the machine is a simple non-super-scalar processor with fixed instruction code. That is your assumption. The second one is realistic machines have deep pipelines, I cache, T cache, etc. That is again your consideration here. So, you define the cost of instruction as, this is one is basically for the opcode cost. Okay. That one is opcode cost plus cost of source mode plus cost of destination mode. Now, the source mode, to compute this cost only, whatever we have done earlier is going to be referred to. Okay. So, this is what you are going to refer to for computing the cost of source mode and computing cost of destination mode. So, other than that, it is going to be 1 plus cost of source mode plus cost of destination mode. Okay. Now, on to an example here. Okay, let us take this, move R0 comma R1, that is, this is your source, this is your destination. So, this 1 here is for the move. So, we already know that if it involves R0 or R1, it is not going to cost you anything. So, its cost is going to be 0. So, it is 1 plus 0 plus 0, which is again 1. What does it basically say? Store the contents of R0 into the contents of R1. So, move basically means transfer or load. Okay. So, load the contents of R0 into the contents of R1. Now, what is this basically? Move R0 comma M. So, this move will cost you 1 unit cost. R0 is not going to cost anything. M will cost 1. So, it is 1 plus 1, which is going to be 2. That is what is available here. So, which simply says store the contents of R0 into a memory location M, which probably say move R0 comma variable A. So, what does it basically say? A is a variable which is available in a location, in a memory location, and I have to move the contents of R0 into the variable A. So, that is going to be costing you 2 units. Now, the next one is move M comma R0, which is a reverse of this, that is this is your source. It is something like move A comma R0, that is get your value A available in a location, in a memory location, and then store it in a register R0. Again, this is going to cost us 2 units, because this M involves a unit cost, this move involves a unit cost. So, 1 plus 1 is 2, R0 involves no cost, which is 2. Then the next one is move 4 of R0 comma M. So, this is actually register based, right. So, we have just now seen it is not move C of R0. So, C plus contents of R0, that is 4 plus contents of R0 into M. We know this 4 comma R0 is going to cost us 1, this M is going to cost us 1 more, which is 1 plus 1 2, and this move is going to cost us 1 more, which is going to be 3. So, therefore, the cost of this instruction is 3. Now, the next one is move star of 4 comma R0, 4 of R0 comma M. Again, move is going to cost us 1, this M is going to cost us 1. How do I get this 4 of R0, which is nothing but contents of 4 plus contents of R0. So, here it is simply 4 plus contents of R0. So, it is going to be content of 4 plus content of R0. Again, this is going to be costing you 1. So, 1 plus 1 plus 1, which is going to be 3. Okay. And then move hash 1 comma R0. So, move is going to cost us 1. We already said hash 1, that is the immediate operand will basically cost us 1 more, which is going to be the cost 2. Now again here add 4 of R0 comma star 12 of R1. So star 12 of R1 will be 12 plus contents of R1, the content of that, okay. So this is actually indirect register index, okay, and this is nothing but indirect register, okay. So 4 of R0 to this one. So again add is going to cost us 1 unit. Our assumption is each of these instructions, move or add, whatever is going to cost us only 1 unit. So 1 plus 1 plus 1, it's going to be 3 cost. So before determining whether this is the sequence of instructions to be to be generated as part of your input, we have to look at the cost and then you have to check whether is this cost okay to generate the instructions or not. So this will be used as a basis for your final code which is going to be generated. So this is just an example. We will be following this convention throughout for all our code generation algorithms. Let us look at this. So instruction selection is going to be important to obtain efficient code. Suppose we are going to translate the 3 address code x is equal to y plus z to move y comma r0, add z comma r0 and move r0 comma x. So I am going to move y comma r0, then I say add z comma r0 and then move r0 comma x. So y is moved to a register, z is added to the register content and then I am going to say assign it to x. So how does this basically work? So here in this case move y comma r0, add z comma r0. So this is fine. Now supposing if I have this instruction a is equal to a plus 1, that is if I am going to generate here the code corresponding to this expression in a similar fashion as this. So what will I do? I will move a comma r0, add hash 1 with r0 and then move r0 comma a, okay, and move r0 comma a. So this is what we are trying to look at here. Now this is going to cost us 1, the first instruction is going to cost us 1, second again 1, third again 1. So this is going to cost us basically this 1 here is a for a and this for move is 1. So 2 again, here again it is 1 for this one and add will be again costing you 1 more. This a will cost you 1 plus a move will cost you 1 more, which is 2. So each instruction here costs you 2 units. So totally you have to have 6 units for computation here. On the other hand, if I simply say increment a, okay, increment a is going to cost us only 2 units because increment is going to cost us 1 and I am involving a memory, therefore it is going to be costing you 1 more. So the cost is going to be only 2. That is what I am doing here, that is adding 1 to a and the result is also stored in, adding 1 to a, the variable a is getting a value a plus 1. So that is going to be 1 costing you 2. One more is add hash 1 comma a. This is involving a memory here. So a memory here which is going to be costing you 1 plus 1 and this add is going to cost us 1 more which is going to be costing you totally 3 units. So this 3 and here it is going to be only 2 which is much better than the 6 which is going to be costing you here because we kind of used this as a basis for generating code for even this instruction. So a is equal to a plus 1 can be dealt in a much simpler sense here. So therefore the choice of instruction is going to basically be a big difference here in final code generation. Now again addressing modes again is going to basically be a real task. Suppose we translate a is equal to b plus c into this instructions, move b comma r0, add c comma r0, move r0 comma a. And supposing say the addresses of a comma b comma c are stored in r0, r1 and r2, okay, assuming it is already stored, then move star r1 comma star r0, add star r0 comma r2 comma r0. That is what am I doing here? R0 has got a, r1 has got b and r2 has got c, okay. So I will simply say star r1 is moved on to star r0, okay, because anyway I am going to rewrite a. So I can reuse the register corresponding to a here which is r0 and then I am adding r2 with r0, that is r1 has got b, r2 has got c. I can use these two, add it to compute it into r0 back. That is what I have done here. So r0 is assumed to be held by A, but it is now removed of that, because anyway I am going to recompute A to with the value of B plus C. Now here if R1 and R2 contains values of B and C, okay, here addresses are stored in these results. So therefore I use the star, which is indirect register operand. Supposing R1 and R2 contains values of B and C, here I will do what? Add R2 comma R1 and move R1 comma A. So I can simply add directly using the two registers. Now this will be very cheaper. So I have to the first instruction costs only 1 unit, second will cost you 2 units. So 1 plus 2 is going to be 3 units. Okay. So depending upon the addressing mode also, you can basically select your instruction. So for example, again this is going to be involving some global code optimization also. Our 3 address code to assembly code should support or should be in a position to perform global code optimization also. For example, same instruction converted like this. This is 2 instructions. We are going to convert it like that. For example, B plus C is move A comma R0, B comma R0, and then the result is stored back in A. Okay. And again here move A comma R0, because looking at the instructions individually, not looking it at as a link. Okay. So here move A comma R0, add E comma R0 and move R0 comma D. That is, if I have RHS will definitely have 2 operands and an operator, I will move one operand to a register and the other operand with the register which has been got this earlier operand, and then store the result back into your variable. So this is what is the 3 instructions corresponding to the first statement and the second statement. Okay. Now what happens here is I am using A here. So anyway at this point itself R0 has got the value of A. Okay. So therefore this instruction move A comma R0 is going to be redundant, and I need not move here again A comma R0, I can use the same value itself. Okay. So at least I want to store the temporary value of A into R0, this is fine, R0 comma A is fine, but again moving A comma R0 back is going to be redundant, because R0 already has a value of A. Okay. This is fine and the next one is also fine. So how do I get rid of redundant instructions? Is going to be another job in choosing your sequence of instructions. So in addition to the next issue is register allocation and assignment. Efficient utilization of the limited set of registers is important to generate final code. You have only limited number of registers, but you have infinite number of variables. So how do I do it? Typically it is done by 2 or 3 methods. One particular thing is to select the set of variables that will reside in registers at a point in the code. So you will determine which point of your code requires which variables. Based upon that you can basically allocate your registers. Second one is you have to pick the specific register that a variable will reside in at a particular point of time. So you can say that I will assign register variable A to register R0 only. I will say I can assign variable B to register R2 only, etc. Supposing how do I to simply say it, how do I compute it? Supposing the variable A is going to be used throughout in your program more number of times, okay, then it is better to allocate variable A a particular register rather than allocating and deallocating that particular register at any point of time. Okay. So depending upon which variable is going to be used more number of times and which variable's value is going to be required at a later point of time, you will put it in a permanent register. So that is one simple way. We have methods like graph allocation method. We also have some Chaitin's algorithm, Briggs algorithm for register allocation and assignment. So in this course we will see 2 algorithms. One is the graph allocation algorithm, a graph coloring based algorithm, and the other one is based on use and liveness information of variables. How do I allocate registers? Now let us take this case. This is basically consider T is equal to A plus B, T is equal to T into C, T is equal to T by D. Okay. And here again consider T is equal to A into B, T is equal to T plus A, and T is equal to T by D. Now look at these 2 codes separately. The variable T though it is temporary, it is used more number of times here in this piece of code. So, I can allocate register R1 for the variable t. So, what have I done here? Move a comma R1, add b comma R1, result is now in t. Okay. So, I need not store back and forth this variable t. Okay. So, I can simply say multiply c comma R1 and then divide d comma R1, result is put back into t from R1. That is what I have done here. Similarly, here I have used the variable t is used twice, variable a is used twice here. Okay. When you have a variable as part of the RHS, you call the variable as being used. Okay. And when you are defining some variable on the LHS, it is called as variable said to be living or is getting defined here. Okay. So, I have R naught as a and R1 is equal to t. So, when I am assigning like this, I am preventing back and forth movement from register and to register. Okay. So, what does it basically say here? Move a comma R naught, move R naught comma R1, multiply b comma R1. Okay. Why is the move here? Because I have already said R1 will be in t. So, rather than using that as a separate one, I can basically compute it. I can also do it another way. I can simply say move b comma R1 also, and I can say multiply a comma R naught comma R1. So, result will be in R1. That is also another way of writing the instructions. Add R naught comma R1 is the next one. Okay. And then I will say divide d comma R1 and then move R1 comma t. So, that is what I have done here. So, depending upon how many times a particular variable is used, I can allocate registers accordingly. The next one is choice of evaluation order. Computing one instruction is separate, computing independent instructions without any order will also help generate good code. So, for example, here move a comma r, okay, let us take the instructions. T1 is equal to a plus b, c plus d, e into T2, T1 minus T3. So, for this I have got code which is sequential, and I have used here, I have used only two registers R0 comma R1, but I have actually moved back and forth. Okay. So, because T2 is to be used here, I have actually moved the result back into E and so on. So, this is A comma R0, B comma R0, move R0 comma T1. So, R0 is getting, I have transferred R0 here. Okay. So, rather than doing this, if I could change the evaluation order, I could avoid moving back and forth from registers. So, example is here where I have got, I am computing C plus D earlier. Okay, I am computing here C plus D earlier, where I have moved when instructions are independent, their orders could be changed basically. So, I have moved C plus D first. Okay. And then anyway I am going to multiply R0 with R1, so I am using that and then do the remaining computation. So, changing the orders. So, C plus D is done first, and then I have E into T2, then I have A plus B, then I have T1 minus T3. So, this is what we are doing here, where I could change the order to reduce number of instructions. So, this has got now 3 plus 2, 5 plus 3, 8 instructions, whereas the previous one had 3 and 6, 10 instructions. I have reduced 2 instructions basically. So, this is also possible with respect to code generation. Now, the primary task of this, the first step in code generation is to construct what is called as a basic block and a flow graph. A basic block is a graph representation of 3 address statement, which is called as also as a flow graph because it depicts flow of information from one basic block to the next basic block. The nodes in the graph correspond to a sequence or a set of computations, and the edges in the graph indicates a flow of control. That is how information flows from one to the other. That is what is available as edges. So, blocks will have a sequence of statements, could be 1, 2 or more. Now, how do I separate basic blocks? What is my input to basic blocks? That is going to be an important task. And this is necessary for optimization of code as well as for register allocation. I told you about this use information and liveness information, liveness in terms of whether a variable is said to live or not live. So, that is what we are looking at as register allocation with reference to basic blocks here. Now, a flow graph is a graphical depiction of a sequence of instructions, It can be defined at the intermediate code level or at the target code level. It can be done in both ways, both levels, at the intermediate code level or at the final code level, where it is useful for optimization. Example is here, where I have move 1 comma r0, move n comma r1, jump L2. This is at the final code level. I say a jump L2. So, I will have an arrow from here to here indicating I have a jump. Okay. And then here I will say jump on no 0 r1 comma L1, where I will go back to L1. So, I am depicting it here. So, this is called as a flow graph. Okay. Now, basic block is a sequence of consecutive instructions with exactly one entry point and one exit point, okay, with a natural flow or a branch instruction. So, here let us take this. I have, this is my sequence of instructions. Again, basic blocks can also be constructed either at the intermediate level or at the final code level. So, I have it at the intermediate level here, I have it at the final code level here, where I have move 1 comma r0, move n comma r1, jump L2. It should have one entry and one exit. So, one entry and one exit there, where it jumps to L2, again it is going to go back to L1 here. Okay. So, this will again have one entry and one exit point. Okay. So, this is what we are trying to look at as an example. So, this can also be a basic block. So, these three instructions will form one block, these two another block, here that's going to be the next block. Okay. So, now successor and predecessor blocks. Suppose the flow graph has an edge B1 to B2. B1 is a predecessor of B2 and B2 is a successor of B1. So, in that case, this block, the block corresponding to L2 has an edge from this block. So, this block is a successor of this block, whereas this block is going to be a predecessor of this block. So, that is going to be a simple example. So, this is just a definition of basic blocks here. Now, how do I construct the basic block? There is a small algorithm here. The first statement is a leader. Target of a conditional or an unconditional num is also going to be a leader, and statement that follows immediately after a go to is also going to be a leader. So, and for each leader and its basic block, you will have to construct a sequence of instructions that is going to belong to that particular basic block. So, to summarize this module, we have looked at the need for code generation and handling the various issues in code generation, and the basic block and algorithm for basic block creation was also discussed here, and this can be done at the final code level or at the intermediate code level also. Thank you.